Dear students, welcome to another lecture on elements of machine design. Yesterday, I shared that file, Excel file containing your attendance. I want to bring to your notice that the email that you are using, let it be the email that is registered with us. Otherwise, what will happen is, even though you are attempting the quizzes, you may be marked absent. Then you will have to again contact us, and again we will have to look into it, and it is all waste of time. So I request you to use the registered mail that you have, that is registered with us. And also, another thing that I want to say is it just don't attempt the quizzes. First, you see the video lecture that I am sending. You see it. You see, every day you see it, you understand it. If you are unable to understand, you see it the second time and then attempt the quizzes. Then you will be able to answer. You try to get, if I giving 5 questions, get 5 out of 5. If I give 10 questions, get 10 out of 10. You see. And if something is wrong, you just try to understand why you have made that mistake. You see, unless you have, you do proper learning, then you will not be a good engineer, and you will not be happy in whichever job you go. You see, the confidence you will get in your job when you have thorough knowledge of the work that you are doing. Otherwise, others will make fun of you, and you'll be frustrated in life, always depending upon others, because you yourself cannot do it. Okay, leaving it. Now come back to our lecture. So yesterday we have seen the stress strain diagram for ductile materials. I said ductile material, an example of ductile material is mild steel. Okay, that exhibits certain kind of behavior. Now, today we'll see about the brittle material. A brittle material, an example of brittle material, if I should say, the best example is cast iron. See, cast iron, what happens? See, if you take a hammer and hit it, it will break into pieces. And those pieces can be joined together. That means, it will not be that it is a stretching and then breaking. Without any stretching, it will break. Like glass. Glass is another example, good example for brittle materials. You see, when it breaks, it does. You don't see a stretching before breaking. If something is stretching and breaking, that means it is a ductile material. Something is without stretching, it is breaking, means brittle material. So, even though it is metal, the cast iron, if you hit with hammer blows, it will break into pieces. Okay, so that it's a brittle material. So, how its stress strain diagram is? You see, you should see, many times students just draw this curve and leave it. You see, what is on the x-axis and what is on the y-axis, it is necessary to write in your exams. Otherwise, if you just write this much, you see, if 3 marks are there for this curve to be drawn, I will give only 1 mark, because the student has not specifically said what is taken on the x coordinate and what is taken on the y coordinate. Okay, so on the x coordinate, strain is taken, and y coordinate, stress is taken. Again, strain has no units and stress is Newton per meter square, that is the unit. Okay, sometimes it is mentioned in MPa also, megapascals, that we'll see later. As of now, you remember that it is Newton per meter square. Okay, see, now we see that this curve for the brittle material, it goes straight to some distance up to P or something, and then, you know a little bit of um, elongation you see, a little bit of strain you see, and then at B it fails. That's all. You see, and this is not so much as shown in this figure. It is very little plastic. See this range, no, P to B is plastic deformation. Plastic deformation is that deformation when you take away the load, it will not regain its original shape. Elastic deformation is that when you remove the load from the component, it will regain its original shape. Okay, that is the meaning, elastic deformation, plastic deformation. So here we see 0 to P is a linear this thing, and here some point Y is mentioned. Maybe it's an yield point. See, yield point is not clearly demarcated in case of brittle metals, and if you have a little more stretching, it will fail. It will break into two pieces. Okay, not pieces or two pieces, many pieces. It will break like a glass breaks into many pieces. Okay, this is how a brittle material behaves. Okay, see, these are only two curves that we have seen. If you, in case of rubber, it may show some other behavior. Yeah, like that. Different materials may show different kinds of uh, behaviors. But as mechanical engineers, we'll be mostly dealing with uh, like ductile materials like mild steel, and some other materials, like aluminum alloys, copper alloys like brasses, bronzes. Okay, and such things, and also cast irons. Okay, we'll not be studying so much about rubber and other materials. Okay. Ah, okay, coming to the next point. Next point, let us see about the types of stresses. Types of stresses, again, this is one thing which you have already studied. Okay, what are they? Tensile stress, compressive stress, bending stress, and then shear stress. And further, shear stress, it can be divided into two: direct shear stress and torsional shear stress. And direct shear stress also single shear, double shear stresses. Okay, then bearing pressure and crushing stress, that is the fifth category here mentioned. Bearing pressure is one, and crushing stress is one. So these are the different types of stresses that we'll be dealing with in design of machine elements of machine design. Okay, now let us see one after the other. Okay, now let us come to the first one is tensile stress. Tensile stress is because of the tension that comes in the component. See here, an example of tensile stress is given. This is a machine element. Okay, and it is stretched. You see this P, this is the P load. This is the P load or force. We are pulling it apart. When we are pulling it at this cross section XX, cross section means what? We are cutting across. Okay, this can be a square rod, or it can be a cylindrical rod. Cylindrical rod means its cross section will be a circle, and if it is a square rod, the cross section will be square. It can be a rectangular rod also, then it will be cross section will be a rectangle. We are not sure, we don't know what type of cross section it has, whatever it is. Okay, if at this cross section, if you cut and make it into two different parts, we will see that internally, because of this force P, this force P is there, no, on both ends. Because of this, some internal lines of forces are acting here. These lines of forces, uh, they are resisting that external load P. Okay, so these internal forces per unit area, mm, that is the stress that is developing. When tensile stress is there, then what is developed is tensile stress. So tensile stress can be given by this formula here. Tensile stress, it is denoted by sigma. You see how the sigma is. Sigma suffix T here. T stands for tensile. So sigma T means tensile stress. Sigma stands for stress. Tensile stress is the resisting force divided by cross-sectional area. What is this? P dash is given. No, it should be the external force P. So here it is written P by A. P is the external force that is applied, or the resisting force. Okay, whatever is this, the same thing will be applied here. Okay, so P by A. Okay, this is Newton, that's just per meter square. So this is the tensile stress. Okay, now coming to the compressive stress. Compressive stress, you see that P is acting in the opposite direction. Yesterday I gave you one question and quiz showing this diagram. Most of the people answered correctly, but there are few who, who did it not right. I don't know whether they don't see the diagram properly, or they make some hurry. They hurry it. You see, you should observe things properly. You see, observation is one essential requirement for a good student. Okay, whether this P is the arrow is to going outside or inside. You see, if it is pressing it, if it's pressing the component, that means it is under compression. Okay, so again at the at the cross section, if we see, you see now the arrows here are in the opposite direction. Hmm. Okay, anywhere, you see, the direction of these internal forces will be opposite to this one, opposite to the external force. Okay, so this will be uh, acting, these internal forces will be acting throughout the cross-sectional area. And this cross section again can be a circle, it can be a square, it can be rectangular, it can be I-beam, or it can be C section, or it can be T section, or any regular object also. Okay, any irregular shape. Okay, but anyway, whatever is that area, you have to calculate. Okay, and if you know the outside force P, and if you know the internal area, then you'll be able to compute this compressive stress. So now compressive stress again is what? Load upon area. As here in tensile stress is load upon area, or force upon area, here also it is force upon area. Force CS means cross sectional area. Okay, force is push, cross sectional area. Okay, load upon area. Simply remember this: any stress, see whether it is tensile stress or compressive stress, sigma is load upon area. Now here, how compressive stress is denoted? Sigma and its suffix C. See, these are the notations we follow. You see, when you're writing C, you should not write it like 6 or something. That vertical, above that circle, whatever is there, that should be horizontal. Okay, not vertical. Some people simply write as 6. Okay, see, it is when you are writing, it is not for your sake alone that you are writing. It is for the others who are going to see your your written material. If they don't understand, then there is no fun. No, I will write like this only, and you cannot say, see, now we are no more students, no more children. The children will be saying, no, this I like, I will do like this only. See, it is not like that. What you should do is, you should write everything in such a way that if some other person, even in your absence, he sees it, he'll be able to understand. So sigma should be this this way, like 6 only, but this that that bar at the top should be horizontal and not vertical. Okay, sigma C. So this is the P is the compressive stress, or the axial compressive stress. As you can see, axial means, see the line that is passing in the center like this, that is called the axis. So axial compressive force upon the cross sectional area. Okay, this is the second stress. And the third stress that we are going to see, is the, okay, I don't know whether you're able to see. I will make it a little bigger and yeah, bending stress. Now this bending stress, I think that you must have already studied bending stress either in mechanics, engine mechanics, or in strength of materials. See, the bending stress, see, suppose there's a bar, there's a beam, or there's a body or a mechanical component, and it is subjected to some bending moment. Okay, this M is shown like this. You see, you can simply say, see, suppose there is a simply supported beam. Simply supported beam means what? Like a rod supported at two ends. Okay, a rod supported at two ends, and there can be a load in the middle or somewhere like that. You see, like from a well, a village, in the village they bring water from the village wells, बावड़ी बावड़ी में से पानी लाते हैं. तो अगर वहां से पाइप पंप नहीं है तो क्या करते हैं वहां पर, वो एक पुल्ली होता है, उसके ऊपर से एक बाल्टी, उसको रस्सी बांध के नीचे डालते हैं पुल्ली के द्वारा और उसको खींचते हैं. सपोज that pulley in the center, along with the load of the bucket and water, is pulling it down, and in the middle there is a rod. Okay, and it is supported to two ends. Okay, so because of the central load, what is happening, that turns to bend a little. Okay, so what is it doing? It is inducing the bending stress there. Okay, see here, you see, this is the front view and this is the side view. From the side view we are understanding that it is a rectangular thing. Okay, rectangular cross section. Okay, and then see, when a central load is acting here, suppose a central load is acting here, what it will do is this will try to bend like this upper fiber, and this will be lower fiber will be bending like this. So the lower, see, and on the middle fibers are all will be going like this. Okay, from here to here, a little bend, a little bend. I'm exaggerating a little. The top will be like this and the bottom will be like this. And if you observe, the top, the bottom thing will be stretched a little, and that means it is experiencing tension. The upper fiber will be experiencing compression. So therefore, what will happen is, you see, this at various stages in that cross section, this bending stress will be varying like this. At one time, one side it will be tension, the other side it will be compression. Okay, see, you need not worry at this stage much about bending stress. See, we'll talk about it later. Okay, and this is the equation that is all important for for determining the bending stress. See, this is called bending equation. These three terms are there. This is M upon I is equal to sigma B by Y and E by R. Okay, what is M? M is the bending moment. I is the moment of inertia. Sigma B is the bending stress. Y is the distance, this one. Okay, Y is the distance of the extreme fiber. He showed here, but it should be the last one. From last to the center. The extreme fiber to the neutral axis. And E is the Young's modulus. And R is the radius of curvature. Okay, so this formula alone you remember for the time being. We will see further afterwards. Thank you.